Determination of solution pH. pH is how acidic or how basic something is. So if you look around your house, can find drain cleaner is marked caustic, as are your window cleaners around your house, your oven cleaner, and your bleach. If you splash a drop of salad dressing in your eye, it burns. So the question is, how can we figure out how acidic or basic something is, and therefore how much potential damage it could do to your skin or to your clothes if it was left in contact long enough? It is definitely not like in the movies where if you get concentrated acid on yourself or concentrated base on yourself, you start smoking and you turn into a pile of goo and it just dissolves you. It doesn't work that way. That's a little Hollywood license there. But you do want to be careful with acids and bases, and you want to be more careful, of course, the more strongly or more concentrated the acid or the base is. So in this lab, we will measure some different concentration acids and bases and measure them via different methods. So there are a few different sets of definitions, but the simplest definition, the one that we'll use in this class, is that acids give H plus when they're dissolved in water, and bases give OH minus when they're dissolved in water. This is out of chapter 8. Some textbooks do overemphasize the point that H plus doesn't really exist in water. It exists as H plus plus H2O, aka H3O plus, the hydronium cation. Certainly when I took chemistry, they didn't bother mentioning this. It was just H plus in water, and that was fine. And I think for us, that's totally fine too. But if you see H3O plus written, just realize that's an H plus in water, expressed as the more realistic, more true to reality form of that cation. So strong acids and strong bases, just like out of the electrolyte lab, the light bulb experiment, has nothing to do with concentration and has everything to do with how much ionization occurs. If you have a strong acid in water, it's going to 100% arrow only to the right, result in ions. There's not going to be any molecules of acid left. If you have a strong base, the same thing. It's going to be full ionization. All of the ions will result. There won't be any of the undissociated molecule or ionic compound left. We have examples here with hydrochloric acid, old school name muriatic acid, and sodium hydroxide, otherwise known as easy off oven cleaner in your house. So each of these, strong acid, strong base, fully ionizes in solution. And so if we have a measured amount of HCl added to our solution, we will have that amount of ions present in our solution. Weak acids and bases, again, has nothing to do with concentration, doesn't have anything to do with how much acid or how much base is there. It's a question of how much ionizes. So acetic acid, which we'll do another lab on later, otherwise known as vinegar, only partially ionizes. We have the arrow going both directions. Ammonia dissolves in water wonderfully and results in a small amount, as you saw in the light bulb experiment, of ammonium cation and hydroxide anion. There are both ions and molecules present in solution when you throw the weak acid or the weak base into water. The double arrow indicates an equilibrium, which is out of chapter 7, that you have molecules forming ions and you have ions forming molecules. And in this lab, and in most cases when you're dealing with water, H2O, as a reactant or a product, it's very, very helpful to think of it as HOH, an H plus and an OH minus. Even though, as we saw in the light bulb experiment, water does not ionize. It is a non-electrolyte. That being said, it could be made to dissociate, made to ionize by being in the presence of a base or an acid. And when it's involved in a reaction, it's very helpful to think of water as H plus and an OH minus, HOH. Concentration, what strong and weak have nothing to do with, is how much do you have, just like the concentration of anything. I did have it on an exam once. A student tell me that concentration was focusing intently. They had clearly Googled the definition of concentration or looked at dictionary.com or something. That is a definition of concentration. It's just not the chemistry definition. So make sure you answer the question in the context of the class you're in. Okay, concentration for us is how much is present. Many, many, many concentration units could be parts per million, could be percent. The most common one, the one that's most useful when we're dealing with chemical equations, is molarity, capital M, moles per liter. A big M means moles per liter. It also means mega, but based on the context, you'll be able to tell what it is. Moles per liter. It's a conversion factor, possibly. If you find moles and you find liters, you can find molarity. If you have the molarity and you have a certain number of liters, you could find moles. If you have the molarity and you have a certain number of moles, you could find liters, and so on and so forth. pH is just a shorthand. It's a way of talking about concentration without using exponents. Remember, back in the old days, as recently as 30 years ago, typing superscripts and subscripts was a royal pain in the butt on a manual or electric typewriter because you had to reach up and roll the paper up or down. So we wanted to avoid superscripts and subscripts whenever possible. And using the concept of pH, that's one way of doing it. Having the negative log of the concentration, which you don't need to worry about that math in most of the lectures, but your professor, of course, could choose to be different. The negative log of the H plus concentration is the pH. The P of anything is the negative log of that thing, okay? H plus is written in brackets here, meaning concentration. If we were dealing with electron configuration, it would indicate the noble gas core. That's what brackets indicate there. Here, a bracket indicates concentration of H plus. We take that value, take the log of it, and then make it positive, changing the sign, because it'll usually be a negative number because these are low concentrations. That gives us the pH. You may or may not have to do any pH calculations in your lecture. If we want to do a pOH, we would take the negative log of the OH minus concentration. If we want to do a pK, we would take the negative log of the K, the equilibrium constant. So you can either do this calculation or just believe me that it's true, that if you have a negative log of 1, that's a pH of 0. If you have a negative log of 0.1, that's a pH of 1. If you have a negative log of 0.01, that's a pH of 2, and so on and so forth. So long as this is a 1 here, the negative log of it is just the number of decimal places involved. Okay, 1, 2 decimal places. So since these concentrations are usually going to be small, if we take the negative log of it, we can get rid of all the decimal places. We can get rid of writing it as an exponent. This is 1 times 10 to the minus 7 written here. This is 1 times 10 to the minus 2. This is 1 times 10 to the minus 1. 1 times 10 to the 0. Notice that in each case, the exponent is the pH. pH can be measured a variety of different ways. You could use a pH meter, you could use a pH indicator. We're going to try a few in the lab and see if they match or not. Things to think about as you do the lab, as you perform the lab. You got to be careful with the pH meter probe tip. It's made out of glass and can be easily broken. Carbon dioxide, when it dissolves in water, produces carbonic acid. So if you leave your solutions open too long, they can get more and more acidic. And so all of these things have to be taken into account as you perform a lab that's involving pH. So that's the end of the pre-lab material for Experiment 12. Your instructor will give you further details in the lab. Enjoy.